Hi. The fourth theme of the course is the unified approach to efficiency analysis, referred to as stochastic non-parametric envelopment of data, often abbreviated as StoNED. So we have thus far considered the classic approaches, data envelopment analysis and stochastic frontier analysis. So the purpose of this fourth theme is to bridge the gap between these two approaches. Like in the case of the DEA approach, I will start first with the application of the StoNED approach to illustrate you what can we do with this method, and then later I will go to the more practical details how to actually estimate the method. So let us consider again this empirical example of Finnish electricity distribution networks. So now we finally get to the model specification that was actually used by the Finnish energy regulator during the regulation period of 2012 to 2015. So to highlight the fact that we are combining essential features of both DA and SFA frameworks, I have here highlighted with the red color the axiomatic non-parametric specification of the cost frontier C. So like in the axiomatic DEA, I will assume that this cost frontier is monotonic increasing and convex and satisfies constant returns to scale, the three classical axioms of the non-parametric approach and DEA. But instead of assuming away noise, I will keep this SFA style composite error term consisting of both an asymmetric inefficiency term U and random noise term V. And as a bonus, we can also include here contextual variable Z. However, today in this lecture, I will not go into details of that. I will save that to the theme number 5, where we will discuss this contextual variables in more detail, including the DA and SFA approaches to modeling the Z. So my presentation will be based on my 2012 article in Energy Economics. So let us first start from this non-parametric cost frontier C. So unlike in the parametric approaches, we do not have an explicit functional representation of the cost frontier, like in the case of DEA. However, we can of course consider what kind of shadow prices we have for this cost frontier. So we can think about the marginal cost. So what is the marginal cost of output? And remember, in the case of DEA, we have this multiplier weights gamma that we can use in the multiplier formulation of data envelopment analysis. In a similar way, we can get this kind of multiplier weights in the StoNED approach. And in this table, I have normalized these multiplier weights so that they have a meaningful units of measurements. So I have normalized the energy transmission as cents per kilowatt hour. I have the length of networks in euros per kilometer, and customers I have euros per customer. So this can give us an idea of what this shadow price is, what are the marginal costs of these three output variables. And like in DEA, every observation is allowed to use separate shadow prices. So in principle, in the model, we will allow for n different vectors of shadow prices for these outputs. So this table summarizes, so we have some descriptive statistics like the sample mean, sample standard deviation, median, mode, minimum and maximum. This is something that we can report in an empirical paper, for example. We do not have just a single parameter representing the shadow price, but we have a distribution for each output variable. So, of course, these shadow prices, they characterize the cost frontier, and we have three output variables, so we can actually also graphically illustrate how the cost frontier looks like. And on this slide, I have done that. So here we have three dimensions of representing these three output variables. And I have here normalized the frontier such that the total cost is equal to 1 million euros. So in a sense, we are asking what kind of output combinations are possible if the total cost is restricted to 1 million euros. So what are the efficient output combinations on the cost frontier? And so the cost frontier is a piecewise linear frontier, exactly like in the case of DEA. And as you can see from the shape, in the output space, it is satisfies free disposability. It's a monotonic, and it's also a convex. So this would be the output set with the given set of 1 million, given cost of 1 million euro. So if you think about the interpretation of the output set, notice that in the bottom right corner I have indicated there are the rural networks, networks operating in rural areas. So there obviously the number of customers is relatively small. However, the length of network is relatively high, and because the number of customers is small, also the energy transmission is relatively small. If we proceed further to the more suburban and urban areas, so in the left corner you can find the urban networks like the one operating in the city of Helsinki. So in the urban networks, more densely populated areas, the number of customers is relatively high, but because of the more densely populated area, then the length of networks is in relative terms smaller. And as the number of customers increases, the energy transmission tends to increase also almost directly proportionately. And then you can find also on the top of this diagram so-called industrial networks. So with these industrial networks, the energy transmission is very high, but the number of customers is relatively low, and also the length of network is relatively low. So the industrial networks could be, for example, some small towns where is some industrial user that uses very much energy. One example in this sample is also the Helsinki-Vantaa airport is one of the industrial networks. So the number of customers with this such kind of industry network is very small. Also the length of network is relatively small, but the energy consumption is high. So if you think about this kind of output set, I believe it's quite natural that there is this kind of structure with the rural networks, urban networks, and industrial networks in the sample. So in the next slide, I have just highlighted further. It's the same figure. Unfortunately, here the labels are in Finnish, but never mind. It is just the same diagram. I have just highlighted here these so-called efficient facets. So those facets where actually most of the observed data are located in. So you can see this kind of almost like an arrowhead shape or boomerang shape, which characterizes the efficient output frontier in this case. So it illustrates this kind of very high correlations between the output variables, but they are not perfect as we move from the rural networks towards urban networks, and then to move further to the industrial networks. So I repeat, most of the observed data points are then projected to these facets indicated with the red color. And it turns out that actually these shadow prices are very heavily clustered to certain segments. So it's good to point out here that those shadow prices that I indicated earlier, so each of this kind of a segment or hyperplane or facet, if you think about some kind of facet indicated here with a red color, so there would be some unique set of shadow prices characterizing that kind of linear segment of the frontier. And in the next slide, I have actually organized these facets or grouped these different distribution units to these kind of unique facets. So it turns out that there is actually 9 different facets that are very common, and then there is for six units they will get some own unique facets, which is this group number 10. So for example, there is this group number 1 includes 11 firms, and they have this, all these 11 firms have exactly the same shadow prices or marginal cost for the output variables as indicated on the first row. So all those 11 firms get exactly the same multiplier weights. For the second group, which is the largest one, it gives 36 units. So this is the biggest subgroup of units get this also the same shadow prices. So you can also recognize here that that comparing this, what is the relative cost of the energy transmission, network length, and the number of users. So obviously, for those urban networks that are located in most densely populated area, so the shadow price of the number of users should be high. So that would be the group number 7. Notice group number 7 includes three companies. Those are the companies located in the most densely populated areas, and there the number of users has the highest shadow price of 60 euros per user. Whereas then energy transmission and the network lengths have relatively low value. So the logic is very similar to the DEA. Remember that in the DEA, DEA allows the companies to find the multiplier weights that show the performance of the unit in the most favorable light possible. And there is the similar logic exactly here also when we apply StoNED. So the evaluated units will be projected to the facets which show the performance in the most favorable light. In fact, if we would allow these companies to choose themselves that, okay, we could give this kind of menu of shadow prices, and companies could choose whichever shadow prices they would want to use. In fact, it would be in their advantage to choose exactly to the same group that we have already chosen on their behalf here. So these are this kind of most favorable shadow prices that can be given exactly in the same way as in DEA. So in this sense, this non-parametric estimation of the shadow prices is totally in line with this kind of benefit of the doubt weighting of DEA. However, the main difference concerns here that we do not attribute all the deviations from the frontier to the inefficiency. We also allow for the noise term. So let us turn to then this decomposition of the deviations. So like in the SFA case, we can now decompose this deviations from the frontier to the two parts, the inefficiency component U and the noise term V. And to do that, we generally need to impose some distributional assumptions for U and V. And in this application, I have assumed these classical SFA assumptions that inefficiency U is half normally distributed, and noise term V has a normal distribution. So I will get into more detail how we do this, both this frontier part and the inefficiency part later. But as you can see from this table, in StoNED we can similarly decompose the total deviations from the frontier to the inefficiency part and to the noise part. And by comparing this sigma squared U, the variance of the inefficiency term, and sigma squared V, the variance of the noise term, we can see that approximately 2/3 of the variance here is attributed to the inefficiency term and 1/3 is left to the noise term. We can also estimate what is the expected value of the inefficiency term and translate that to the percentage efficiency. So we find that the expected value of cost efficiency according to the StoNED estimation is 89%. So remember that in the case of DEA, we found that cost efficiency was about 80% with the parametric corrected OLS, it was only 60%, and then with the translog functional form with SFA, it was extremely high, but then again we failed to find any kind of real efficiency differences in that case. We can also apply this John Rowe Lowell Matros-Smith formulation to estimate firm-specific efficiency, although this was not something that we did in the application to the energy distribution networks, and I think I will explain that later why that is the case. But if we want to do it, we can do it. So here I have, in this diagram, I have illustrated the distribution of the firm-specific efficiency estimates. So here on the horizontal axis I have cost efficiency, and this is the cumulative frequency distribution of these estimates. So we can get also the efficiency scores out of the data if we want, conditional on the deviations from the frontier. So this illustrates that it is possible to combine the essential features of DEA and SFA into the same framework. So to summarize, as I see it, the main advantages of the StoNED approach are indeed that it's a very natural way to combine the DEA-style axiomatic non-parametric frontier with the probabilistic SFA-style model of inefficiency and noise. And indeed, I want to also highlight that the classical specifications of DEA and SFA are actually obtained as the restricted special cases of this kind of more general encompassing unified frontier model. And perhaps as the biggest advantage of this approach is that it opens door to combining insights from econometrics, economic theory, operations research, and management science. So it truly allows us to apply the entire toolbox of efficiency analysis in a unified and systematic framework. I believe this is the biggest advantage, but unfortunately, it has not been really effectively utilized so far. If we think about disadvantages, well, for me as the method developer, it's very difficult to see any disadvantages. But in practice, I can see that obviously the method is more demanding for the user, and it's also more demanding for the computer. So it's much heavier from computational point of view. And now, after 14 years since I published the first working paper proposing the method, I a little bit regret the silly acronym, which has also it surely attracted a lot of attention, but also some of that attention was kind of negative and has also caused some prejudice against the method. So here in this slide, I have indicated the silly acronym as green color. It's kind of questionable. Is it advantage or disadvantage? But definitely it has also like open door for a lot of unnecessary critique and all kinds of hypocritical critique. So at this point, I want to highlight that this acronym doesn't actually refer to use of narcotic drugs, but it's more appropriate to interpret as a reference to the capital punishment, namely death by stoning. This is more or less how the method has been received in the literature of efficiency analysis. So it's literally stoned method, but not dead. Here I am still making these video lectures about it. So in the next lesson, I will then go in more detail to the estimation, that how do we actually estimate those shadow prices, marginal cost, and how do we decompose the deviations from the frontier to the inefficiency and noise components.